In this video, we're going to finish our intro into ligand field theory by examining four-coordinate geometries. So transition metal sites in Td symmetry and transition metal sites that have a square planar geometry, so would be in d4h symmetry, for example. And we're going to start by just reminding ourselves of what the crystal field splitting energies of these different geometries look like. So if we remember, if we look in going from OH symmetry, where you have your EG over your T2G, and these are split by an energy 10dq, which in octahedral symmetry we gave the symbol delta O. As we saw in the previous video, this splitting of the d orbitals is reproduced using ligand field concepts. In Td symmetry, we have the E-type orbitals lower in energy than the T2 type orbitals. These are split by an energy delta T, with all things being equal. Delta T is equal to 4/9 delta O. In four-coordinate d4h symmetry, we find that the EG splits with the dx squared minus y squared, which is a B1G orbital going up in energy, and the dz squared, which is an A1G orbital going lower in energy, and the T2G level split with the dxy with a B2G orbital going up in energy, and the doubly degenerate EG orbitals, the dxz and the dyz, going down in energy. What we'll find is that ligand field theory reproduces the crystal field results for compounds in Td symmetry. However, as we go to d4h symmetry, what we'll find is that depending on the types of ligands coordinated to the metal center, the energies of these orbitals can be vastly different, and the orderings of the orbitals can be different as well. We're going to start by looking at two compounds in Td symmetry. We're going to look at iron 2 tetrahedride versus iron 2 tetrachloride. We're going to start with tetrahedral iron tetrahedride. So in this compound, the ligands are sigma-only donors. Okay. And we can arrange the hydrogen atoms about the central iron in this manner. Now the salps that we're going to use for the hydrogens are going to look exactly like the salps that we used in the case of methane, where we constructed salps for the 4 hydrogen 1s orbitals. And what we found is that the hydrogen 1s salps transformed into A1 plus T2 symmetries. Constructing our ligand field diagram, we're going to put our iron atomic orbitals on the left, our 4 hydrogen salps on the right. You have your 4 P's, which transform as T2, your 4 S's that transform as A1, and then your 5 iron 3d orbitals that transform as E and T2. For here, we have our hydrogen salps, These are lower in energy than the iron atomic orbitals. As we said, they transform as A1 and T2. Starting with the orbitals where there are no symmetry-related bonding pairs, we're going to bring those E-type orbitals over from the 3Ds. We now have the A1 and T2s that we need to make bonding and anti-bonding combinations with. So starting with the A1, we make a bonding and an anti-bonding combination. Like that. And with the T2s, we make a bonding and an anti-bonding combination between the SALCs and the d orbitals. And there's also these 4 PT2s that form combinations as well. But now these can mix in to our T2 stars that we made from the d orbitals. Determining the number of valence electrons from our 4 hydrogens, we have 8 valence electrons, and from the iron we have 6 valence electrons for a total of 14. So adding these in, there's our 8, and then the additional 6 for the total of 14 valence electrons. I'm going to go through and I'm going to plot out the E and the T2 star orbitals that would be generated. These are close in energy to the atomic iron 3d orbitals and are therefore often referred to as our metal 3d orbitals, or in this case our iron 3d orbitals. Before I go through and plot that out, I'm going to note that this ordering of our metal 3D orbitals that we obtain is the same result that we would get from crystal field theory, with that 3/2 ordering and split by some energy delta T. So going through and plotting these out, our E-type orbitals look like this. So these are results from electronic structure calculations, and as you can see, they look just like the dz squared and the dx squared minus y squared orbitals from iron. They've come across as non-bonding because there aren't any SALCs of appropriate symmetry for those E-type orbitals to combine with. Plotting out the T2 stars. These look like this. They're combinations of the T2 iron atomic orbitals and the hydrogen T2 SALCs. Are more covalent in nature, but are not as strongly overlapping as the sigma type interactions that we observed in OH symmetry. Therefore, those T2 star orbitals are not as destabilized as the corresponding EG star orbitals would be if we were looking at this in OH symmetry. One last thing to note is that Ligand field theory, unlike crystal field theory, gives us insight into why the D to D transitions for compounds in T2 symmetry are much more intense than those in OH symmetry. And this is because of mixing of the T2 4p orbitals into the T2 3d orbitals. What this does is this gives these 3d orbitals some 4p character, and therefore you're turning on a little bit of an allowed d to p type transition in those formal D to D excitations. Therefore, those orbitals gain intensity because you have some of this allowed D to P character within those transitions. This is something that we can see when we look at the Ligand field diagram, as opposed to just simply deriving splittings from crystal field theory. Now what we're going to do is we're going to look at iron tetrachloride in Td symmetry. And what we have to be concerned with now is that when we construct our SALCs, we have to deal with the 3p orbitals of chlorine. So we're going to have our 3pZs, which are going to bond in a sigma type fashion. So the SALCs for our sigma type fashion are going to be the same as what we had with the tetrahedride compound. We're going to have an A1 SALC plus a T2 SALC. But now we have our 3px and our 3py orbitals that are going to bond in a pi type fashion. And these are going to form SALCs that have E-type symmetry, T1 type symmetry, and T2 type symmetry. We're going to construct the ligand field diagram in much the same way we did with the OH compounds where we had pi donors, where we're going to take the sigma only molecular orbital fragment and we're going to add in the pi interactions on top of that. As with before, we're going to bring across our non-bonding interactions. Now, as I go through and I make the bonding and the anti-bonding orbitals, to keep this from getting really congested, I'm not going to fully connect from iron to the SALCs. Instead, I'm just going to increase or decrease the energy relative to the nearest starting point orbitals. So here, these T2s, because there's a match between the T2 stars and the T2s here, these just become slightly elevated, but they're still going to resemble our starting T2 stars from the sigma type interaction. Same with these. These are going to be down here. That should have been a T1 for clarity. I'm going to redo that. And then we're going to have our E. And this E destabilized. So it's now an E star because we're overlapping this metal-based E with this ligand-based E here. Determining the number of valence electrons. We have 24 valence electrons from the chlorines plus 6 valence electrons from the iron. So a total of 30 valence electrons going through and filling in the electrons into orbitals. There's our 24 filling the ligand-based orbitals, and then the 6 from our iron 2, 3d6. We have this. And what we arrive at here for the T2 star over E star is the same result that we would get from crystal field theory. So these are close in energy to the iron metal-based atomic orbitals. So these are our iron 3d orbitals, and we reproduce the delta T that we would get from crystal field theory. And chlorine being a weaker field ligand than a hydride, you have a smaller delta T, and that's because we've turned this the non-bonding E in the hydride structure to this anti-bonding orbital in the chloride structure. So you've really reduced the delta T. Going through and plotting these orbitals out, your E stars look like this. So you can see this is what the iron 3dz squared would look like, and the iron 3dx squared minus y squared. And the T2 star orbitals would look like this. So your 3dxz, 3dyz, and 3dxy, while now there is significant pi type character in those orbitals because of mixing in of the pi T2 salx into your T2 stars. We're now going to tackle platinum tetrachloride and d4h symmetry. So a square planar So here we have our platinum 5d orbitals that are going to be involved in bonding to the chlorines, and we have our chlorine 3p's. The chlorine 3pz's are going to bind in a sigma type fashion, and these are going to have salx that are going to have A1G, B1G, and EG type symmetry, and we have our 3px and 3py orbitals that are going to bond in a pi type fashion, and these are going to have B2G, A2G, EU, A2U, B2U, and EG symmetries. For clarity, we're first going to just consider the sigma type interactions, take those results, and then add the pi type interactions on top of that. So starting off with our platinum 5d, 6p, and s orbitals, and then the 4 chlorine 3pz salx, which are sigma type salx. We have the 6p, the 6s, and then the 5ds. Under d4h symmetry, the p orbitals are going to transform as A2u and EU. The s orbital is A1g, and the d orbitals are A1g, B1g, B2g, and EG. For the dz squared, the dx squared minus y squared, the dxy, and the dxz dyz degenerate pair. Our 4 salx go as A1G, B1G, and EU. So the A1G is our in-phase salc. The EU is this degenerate salc. So So EUA, EUB, and then the B1G is this out of phase SALC. Bringing across our non-bonding orbitals. The EGs come across as non-bonding, as does the B2G. And the A2U, corresponding to the 6pz orbital, comes across as non-bonding. Bonding combinations. A1G and A1G star. And this corresponds to the overlap of the 6s with this type of orbital here, and also with the dz squared. We then have these EUs. And then finally, the B1G. So for the d orbitals, we can see how these would overlap. So here with the B1G, dx squared minus y squared, you can form bonding and anti-bonding combinations. The anti-bonding combination corresponding to what that d orbital would look like that. With the dz squared, you would have the toroidal type structure interacting in that plane with the two lobes occupying that area there. So just reorienting this, have your dz squared orbital. And then out of phase, you're going to have your SALCs. Interacting like that. I'm now going to take this and add in the pi type interactions on top of this sigma diagram. As we did before, we're going to bring across all of our non-bonding orbitals. Now we're going to start interacting. We have A2Us that can interact. We have interaction with the EUs. And now we're going to worry about bringing across the EG and the B2G that have SALCs that those can interact with the metal 5Ds. So we get an EG star, and then the B2G. I'm just going to put that down here. You can put that there. When you go through and you count up your electrons, you find that these down here are all occupied, and you have 8 5d electrons left over from platinum 2, which occupy these orbitals. I'm going to expand this in a second here. So these are filled down here, and then we get this for our d orbitals. Okay. And then going through and doing this expansion out. So the way that we've drawn this, that you have your BG star followed by B2G star followed by the A1G star followed by the EG star with electrons in them like this. These EG orbitals one representation that you can make be like that for the 5D XZ. And the 5DYZ. You can also form these into 5D pi type orbitals, where you would have SALT contributions here and here as well, and the orbitals would be admixtures of these two, and they would be off axes binding into those. You have your A1G that we drew before, but just to redraw that. The out of phase combination between the 5DZ squared and the A1G sigma type interactions. This B2G star be the 5DXY, because it's an antibonding orbital. These are out of phase. And the B1G star is the 5D x squared minus y squared. And the out of phase B1G sigma type interactions. Okay. So there's your 5D orbitals. Now, this is one way in which the splittings can be drawn. However, depending on the overlap between the ligand SALCs and the metal d orbitals, the orderings of all of these orbitals down here can be changed. So for example, we could come up with a strong pi donating interaction in this direction, and this could be elevated so that it would be the one just below the B1G star. Come up with another interaction where you have strong donation in the XY plane, and this would come up here. So the ordering of these orbitals is very ligand dependent, and you have to rely on experimental data in order to determine what the correct ordering of these orbitals are in actuality. But unlike in crystal field theory, you can rationalize the ordering of these orbitals using a ligand field approach.